So we're going to start talking about circuits. We've talked a little bit about electricity, and so we have kind of an idea of what that's going to be about. But let's actually use it. So the first thing we actually need to do is define our terms. So what is current? Well, as it turns out, current is simply a flow of charge. We ran out of letters, so we represent it with the letter I. It has units of amps and an amp is equal to a coulomb per second. Now, if we remember our units of charge, that should make sense. If we're saying this is a flow of charge, that's my coulombs, the number of charges flowing in a given time, coulombs per second. So if we're defining current as a flow of charge, we can also write that mathematically, for those of you who've had a little calculus, as our change in Q, change in charge, with respect to time. So all three of these mean the same thing. In terms of actually defining current in the vernacular, we can talk about current kind of analogously to water. So water flows. Current is the flow of water. We can talk about current being a flow of charge as well. So we're going to use this water analogy a little bit. So current is like the actual flow of the stream. Now, does water just flow naturally? Well, let's rephrase that. Does water flow when it's just flat? I mean, we have lakes, but there's no flow there. What is necessary in order to make water flow? Well, we need some kind of gradient, some kind of change. And so we need the same thing in order to make current flow, in order to make charge flow. So we need a gradient of what? Well, water that starts up here and flows down has some amount of potential energy. Remember your physics one? And it comes down, it loses potential energy and gains kinetic energy. Okay, so we have this energy change. There's a similarity here with the term that we've already been using a little bit, but voltage. Voltage we represent with the letter V. And this is where it gets a little confusing, so just beware. Voltage has units of volts, also written as the letter V. So when you're writing your equations, be sure that you're paying attention to the difference between the variable and the unit. Now, we have defined voltage, in a sense, as our electrical potential. So it's not the potential energy, but it's related to it. So electrical potential. We also may see it written as EMF. Now, what does EMF stand for? EMF actually stands for electromotive force. But we just said voltage is an energy, or related to an energy, not a force. So this is one of those cases where our science and our terminology weren't really jiving. Back when Ben Franklin was trying to figure out what all this electricity was about, he recognized that, I mean, we have a force due to gravity that pulls things down, so there must be some force pulling electrons down, current down. So they referred to voltage as an electromotive force, but it's not a force. I just want to make that clear. We'll see EMF. In fact, we'll also see it written as this script E. All of these are the same in terms of if you see it in a problem, if you see it in a paragraph, all of these mean the same thing. But what is voltage by definition? We say it's electrical potential energy per charge. So again, recall that in order to make current, like water flow, we need this gravitational potential energy. So in order to make charge flow, we need electrical potential energy. But voltage, again, we define as electrical potential energy per charge. So if I have a high voltage, that may mean that I have a fair amount of electrical potential energy and a small amount of charge. That can give me high voltage. I can have a huge amount of electrical potential energy and a large amount of charge. But this ratio here tells me that voltage is not necessarily what's damaging. And we'll see in class some examples of this. So current is the flow of charge. Voltage is the electrical potential energy per charge. And another way to think of it is that voltage is like the height of a hill. So if we have our stream flowing downhill, if we have a high hill, we're going to have more potential energy. If we have our lower hill, we have less potential energy, and that affects the flow. Same thing with current. Now, the other term that we need to start understanding is this idea of resistance. And resistance in our equations is going to look like the letter R with units of ohms, represented by the Greek letter omega. So resistance is something that we kind of throw around in the vernacular, but we actually have a specific definition when we're talking about resistance in a circuit. Now, we might talk about resistance in terms of a pushback, or resistance in terms of fighting through something. So when we're talking about resistance in a circuit, what we're really talking about is loss of energy. So we're going to say this is a source of energy loss, or rather a source of loss or conversion of electrical potential energy In other words, remember our electrical potential energy is related to our voltage. So if we lose electrical potential energy, what's happening to our voltage? It's dropping, right? So if resistance is a source of loss of electrical potential energy, it's also a conversion of energy, because we know that energy is never actually gained or lost. We know that energy is actually always conserved. So if we're dropping electrical potential energy, we also call that a voltage drop. So in essence, what we have is current flows And current flows when there is a potential difference, our electrical potential difference. So voltage causes current to flow. And as current is flowing, when it loses energy, anything that causes that energy to drop, to be converted into something else, we call that resistance. So just kind of a few examples of resistors. If we have, say, energy that is being transformed into light, or energy that's being transformed into heat, that's what resistors do. Anytime you plug in an object and it does something, that something is the energy conversion. So we started with electrical potential energy. That's what's coming out of the wall. And that energy is converted into heat, or motion, or sound, or light, or whatever your object is doing. That's the resistance. So real quick, the way that might look in a circuit, we represent voltage with this long and short line. Anytime you see long and short, that's your voltage supply. The long is usually the positive side. So we have voltage and voltage supply. The squiggle is a resistor. And by convention, we talk about current flowing from positive to negative. So this is kind of like the top of my hill and the bottom of my hill. And something else that we need to clarify in terms of the flow of charge, we define current as flowing from positive to negative. But in reality, think about what current usually flows through. It flows through wire, right? So think about your copper wire. Is copper going to have the protons themselves moving through? Are the atoms actually moving through the copper wire? No, copper is a solid. The atoms are in a solid crystal structure. They're stuck. But the idea is that metals, like copper, have this sea of electrons. So the electrons are able to flow freely. Now, what direction are electrons actually going to flow? They want to flow to the positive. This is actually a case where our terminology got ahead of our concept. So we talked about current flowing from positive to negative, and that's because Ben Franklin didn't know what an electron was. And so in reality, charge is flowing, electrons are flowing from the negative side to the positive. But because of our convention that we're kind of stuck with, we always talk about current as flowing from positive to negative. We're talking about the flow of positive charge, even though we know that the protons are stuck and the electrons are what's moving in a solid wire. Okay, so let's talk real quick about what's happening here. We've got voltage at some high point. So maybe we have a 5-volt power supply. And we're going along at 5 volts. All of this is at 5 volts until I come across my resistor, until I come across my source of energy loss. And at that resistor, I get a voltage drop. And then after the resistor, now I'm down to 0. So we can write this as my change in voltage, or my voltage drop. And effectively, my voltage drop is always going from some higher voltage to a lower voltage. Now, this may mean I can have a 5-volt drop if I go from 10 volts to 5 volts, or if I go from 0 volts to negative 5 volts. This voltage drop is relative, kind of like height is relative. So if I'm 5,000 feet above sea level and I drop a ball 1 meter, I still have the same gravitational potential energy as I do if I'm at sea level and I drop a ball 1 meter. Okay, so this is all a relative term. So now that we've talked about voltage, current, and resistance, let's actually talk a little bit about what resistance physically is. So what affects the flow of current? Well, let's say we've got a wire. Now, we're going to want some current to flow through this wire. So what is it about this wire that affects how current is going to flow through it, physically speaking? Well, one of the first, I guess, more obvious ways to look at it is if my wire is thicker, if my pipe is wider, I can get more current flowing through. So I'm going to say things that are affecting resistance are thickness of my wire. And the way we talk about thickness is we talk about the area. Okay, if I have a larger area of my wire, then I'm going to have more or less resistance. If I have a wider area, it's easier for more to flow. So if I have effectively more area, what that means is less resistance. What else affects resistance? Well, if I have to go through the wire for a longer period of time, if I have to travel further along the wire, that's going to be more resistance. Basically, more wire, more resistance. So we can say the length of the material that we have to push through. So the length of the wire, the length of material, that's looking here. So if I have more material, then I have more resistance. So if I increase my length, I increase my resistance. So there are two other things that I want to mention that actually affect resistance. And it may seem overly simplified, but where is current going to flow better? Is it going to flow better through a rubber wire or through a copper wire? I mean, the material itself matters, whether I'm an insulator or a conductor or somewhere in between, semiconductor. So we talk about that in terms of the number and freedom of electrons in the material. Okay, so if I have a lot of free electrons, then I'm going to have an easier time with those electrons flowing. So we can say that this is related to the resistivity. So we represent that with the Greek letter rho. Something else that affects resistivity is also the temperature of the material. So the temperature of the wire. Now, something to kind of consider is that even though it's easier, even though we have more motion when the wire is hot, the thing is, as electrons are trying to move through the wire, they're bouncing around and hitting things. And the more collisions you have, the more you bounce and hit things, the harder it is to actually get through. And we know that when things heat up, we get lots of motion and vibration going. And so if we want to avoid those collisions, we want to avoid those extra vibrations, that means that we want cooler wires if we want less resistance. We get more resistance as the wire heats up. So both of these are related to the resistivity. And conversely, we have something called conductivity. Represented by the Greek letter omega, which is literally just 1 over the resistivity. Okay, if you know one, you know the other. Just one is the inverse of the other. If something has a high resistivity, it has a higher resistance. It resists more. If something has a low resistivity, that means it conducts better. So if I divide by a smaller number, my conductivity goes up. So let's talk about resistance then in terms of the area of the resistor, the length of the resistor, and the resistivity. So we can say resistance physically is defined as, well, if we have my area increasing while my resistance decreases, that means I'm looking at an inverse relationship here. My length increases and my resistance increases, then I have a direct relationship. If my resistivity increases, my resistance increases. So this is actually an equation worth knowing. These are the physical parameters that affect resistance. The material itself, the resistivity, the length of the material, and the area of the resistor itself. So again, a larger area means less resistance. And just to kind of give you a point of reference, resistivity of copper is 1.72 times 10 to the negative 8th, and our units are going to be in ohm meters. Now, I don't expect you to memorize this number. I'm just going to give you a few resistivities just so you have a point of reference, so you know how resistivity of copper compares to, say, the resistivity of rubber, which incidentally is something like 10 to the 13th to 10 to the 16th ohms times meters. So this is a very small number. This is a very large number. So this is the kind of range we're looking at when we're talking about resistivities. So another way to define resistance in terms of voltage and current is we can say it's the ratio of voltage drop to the current across a resistor load. So in other words, we can say that resistance is how much voltage drop we get at a given component for a given amount of current. Now, this is useful, but for ohmic devices, we say that the resistance is constant. So we're going to rewrite that and say that voltage equals current times resistance. This, yet another equation worth knowing, is Ohm's law. So basically, let's pause and think about, say we have a 9-volt battery here with some resistor. So in this case, if we increase the resistance, so if I put in a large resistor, what's going to happen to the current? I mean, I only have 9 volts to start with. So if this is the only energy I have to start with, if I increase the resistance, I'm going to get less current flowing. If I decrease the resistance, I'm going to get current flowing a lot more easily. So I'm going to have a lot of current flowing. So in other words, if I increase my resistance, I decrease current. And if I similarly decrease resistance, then I'm going to increase current. So effectively, I'm saying that the total resistance in a circuit affects the current for a set voltage. So what if I have 2 resistors? Well, I know that matter is conserved, and charge is matter. So we can talk about conservation of charge. We know that energy is conserved. We've already talked about that. So we have conservation of energy that we're considering. We have conservation of charge that we're considering. So when we say conservation of charge, effectively, what we say is that the resistors aren't eating the electrons. The electrons don't just poof go away in a resistor. Electrons move through a resistor. So we can say that resistors don't eat electrons. So in other words, let's go back to our water analogy. We said that current is like the flow of water, and voltage is like the height of the hill that we're flowing down. Okay, how do we convert that energy? So if resistors aren't eating the electrons, if resistors aren't stopping the current or inhibiting the current, what are resistors doing? Well, in a sense, they inhibit the flow, which is what we're talking about here with Ohm's law, but it's not that we're sending electrons in and they're not coming back out. Consider a paddle wheel. So we've got our paddle wheel, maybe our grain mill, and we've got our water flowing down. And as the water is coming to the mill, it pushes this paddle wheel. And the water then comes down and flows away. So if that's what's happening with water, we have some potential energy, and we lose that potential energy as we fall, but that falling motion is what's causing my wheel to turn. So I'm gaining some mechanical energy here. So this is my energy conversion. That's what resistors do. You have current that comes in. The resistors take that energy out, but the electrons themselves continue to flow. So we haven't lost any charge in a resistor. So That's what we mean here when we say that resistors don't eat electrons. So another way we can say this is that effectively current in equals current out for an individual resistor. So another way we can talk about conservation of charge is if we have one resistor in one branch and then we split. So in other words, I might have a case where I say that my current in equals my current out, and that's going to equal the sum of current in all the branches. And we'll talk more about this in just a second. But I want to point out both of these are an instance of Kirchhoff's junction rule. Okay, so conservation of charge is effectively what Kirchhoff's junction rule is about. So let's look at a case where we have multiple resistors, but we're looking at resistors going one after the other. So this is our case A, if you will. So we're going to have some voltage with two resistors. So I'm going to say that this is I1. So it's the current that's flowing into my first resistor. I'm going to say this is my second resistor. And I'm going to say the current flowing into the second resistor is I2. And just for kicks and giggles, because I want to know about the current flowing out as well, I'm just going to call this I3. So I'm looking at the current in three different places. But if conservation of charge holds true, that means that the current into this resistor is the same as the current coming out, which is then the same as the current going into resistor 2, which is the same as the current coming out of resistor 2. So in other words, we say that I1 equals I2 equals I3 when resistors are in series. Now, series is what we mean when we say resistors are one after the other, kind of like a TV series. You don't watch all of the shows at once. You watch one after the other. Okay, so this is resistors where the current has to go one after the other. There's no way for the current to get from here to here without going through my first resistor. So notice in this case, we still only have one battery compared to this case where we have one battery, one resistor. So if I say that I have the same amount of energy in both cases, I have the same voltage in both cases, then let's say for kicks and giggles, I'm again dealing with a 9-volt battery. What that means is, in my first case here, remember we said that that looks like I start at 9 volts, and then I go along, I hit my resistor, and I drop, and I get down to my 0 volts. Now, something I kind of want to point out, this is my voltage drop. Well, Ohm's law says that voltage drop, that voltage is equal to current times resistance. Now, this is true for this individual resistor over here. But now we're dealing with this case where we have 2 resistors. And I still have this same 9 volts that I'm starting with. And what do I end with? I mean, it's the same battery, so I still end with 0 volts. So I'm still going to experience the same total voltage drop. But what that ends up looking like is if I say that this is R1, if we have some voltage drop at R1, and then we're moving along, and then we have our second voltage drop at R2, we still have only dropped a total of 9 volts. So the idea is this is the voltage drop we get from R1. So we can say delta V1 equals my current. Well, we said all my currents are the same. So I times R1. And this voltage drop is equal to my current times R2. And again, I'm just using this individual I because in series, we're saying that all the currents are the same. So what I'm trying to get at here is that in this case, in series, we say that current is constant and voltage sums. So the total voltage I have to start with is equal to the sum of the total voltage drop I get from each resistor. So I can say that my total voltage is equal to delta V1 plus delta V2 plus however many voltages, however many resistors we have, all of those individual voltage drops are going to add up to my total voltage. And again, current is constant when we're dealing with a series circuit. So that's where we have resistors in series, but there's another way we can arrange resistors. So what if I were to do something like this, where I have my battery, but now I go and I split my current. So I have resistor 1 here and resistor 2 here. So again, I'm going to say that I've got this 9-volt battery, and I've got current coming in, but what happens to that current when I get right here? If I have a single electron, a single charge, can it go both ways? Conservation of charge says it can't. I have to pick one route. So if each individual charge is going to be picking different routes, then effectively I can talk about my current 1 and my current 2. Okay, so I have I1 and I2. Just like I had I1 and I2 when I was dealing with resistors in series. But here, are they necessarily equal? What if I have a large resistor and a small resistor? Nature's lazy. Nature does indeed take the path of least resistance. So current is going to be, do you think, greater or less for a small resistor? I would expect a small resistor to experience more current, because Ohm's law says that if I have less resistance for a given voltage, I've got to have more current. So let's talk a little bit about what's happening here now. So once I have current 1 go into resistor 1, we can agree at this point that this is still I1, and this is still I2, that the current didn't change just because I went through a resistor, right? We've established that. But then we have the place where they join back up. And the current after that, I'm going to say, is current out. So this is what we call a parallel circuit, because current can flow in 2 different resistors at the same time. Now, the trick with parallel, the key, you know you have a parallel circuit anytime you have a junction, okay? So a junction is where you have current splitting or where you have current coming back together. So both of these are junctions. And after the junction, the current is split into different branches. So here I have 2 branches with resistors on them. So this is what we're talking about in this case, where we have the current coming in, and that's equal to the current coming out. That's our conservation of charge. Whatever we started with is whatever we're ending with. No electrons were eaten. But we know that not all of these branches have the same current. It's not that current in is the same in every branch. That doesn't work with conservation of charge. But what we can say is that whatever I start with, I split up. So the sum of my currents in my branches is equal to the current coming in. When they all come back together, it's equal to the current coming out. So let's take a look at what that means in terms of our voltage. So let's say that I have, let's look at one individual charge. And it's coming along. It started at 9 volts, just like we've been doing. And just kind of as a quick refresher, we said that when we just have our 1 resistor, it looks like our 9 volts, our drop down to 0 volts. We just have our single drop, right? Now we have 2 resistors. But again, here we are in parallel. Okay, this is a parallel circuit. So effectively, if I have some charge coming in, and let's say this one picks resistor 1. So if I go through this path, I get this drop in voltage. I go from 9 to 0. So that's what I get with R1. So in fact, I'll go ahead and redraw this line. And I'm going to say this is voltage drop 1, and it corresponds to R1 times I1. Okay. Because Ohm's law applies to individual resistors, individual components. So when I'm dealing with Ohm's law, I can't use I1 and R2. That's not how it works. I have to talk about the voltage drop across R1 is equal to the current flowing through that resistor multiplied by that specific resistance. Okay, just so we're clear. But let's say we have a case where we're going to say R2 is, well, let's say R2 is greater than R1. So this is more resistance. Now, if I have more resistance, then that means I'm going to have less current over here. But what does that mean about the voltage drop itself? If I'm an electron and I come in and I pick the R2 path, that means I don't even consider what's going on at R1. This is the voltage drop I see. So at R2, maybe I still go from 9 volts to 0 volts. It may look like a different line, but it's still the same height. It's still the same loss of energy. And so what I'm getting at here, so we can still say delta V1 is R2, sorry, excuse me, delta V2 is R2 times I2. But the thing is, we're saying that delta V1 is equal to delta V2. So think about going to a water park. And you've maybe gone to Hurricane Harbor or one of those places. And you go to the tower where you climb up. And when you get to the top, you have 3 options of slides to go down. You can go down the slow kitty slide or the black slide of death, or you can go down kind of the mediocre blue slide. Okay, so that's where we are. Think about your potential energy. You've gained some amount of gravitational potential energy just by climbing the steps. Your height is the same regardless of which slide you pick. And all 3 end up at the same kiddie pool at the bottom. So you lose the same amount of energy regardless of which slide you take. Now, you obviously pick different slides for different reasons. I mean, you get different results going down different slides. One you get down really fast, one you get down kind of slow. One, a lot more water can go through, one maybe not as much. But the idea is it's still the same loss in energy every time. Same thing is going to be true with our resistors in parallel. Whenever I have a junction, that's like me at the top of the slide and I get to pick. So whichever route I pick, I'm still going to have that same voltage drop as if I had picked any other branch. Okay. So what I'm getting at is that in parallel, effectively what I'm saying is that it's my voltage, my voltage drop is constant, and it's my current now that is summing. So in other words, my current in equals I1 plus I2 plus I3, however many branches I have, how many branches with resistors I have. All of those currents are going to sum. And again, this equals I out.